So we're going to continue on here and look at what happens in terms of the accessory organs. When we're talking about the accessory organs, we're talking about the liver, the gallbladder, and the pancreas. The accessory organs that we're talking about here are going to produce secretions either to neutralize gastric juices, form a protective mucus, or digest the major macromolecules of proteins, lipids, and carbohydrates by releasing enzymes that will go into the alimentary canal. So let's take a look at the function of the liver here. So the liver is going to, as we talked about with excretory function, as a means to go ahead and clear toxins from materials that are being ingested. It's going to be the first site for absorption of carbohydrates and free fatty acids following absorption of materials from the mucosa of the alimentary canal. It's going to trigger all secondary messenger pathways, all of the endocrine responses that we see within the body following digestion of the meal or the postprandial area. The whole entire function of the liver in terms of its function here is going to be based off of the first pass system that it gets due to the anatomy of the vasculature as it exits out from the alimentary canal. So if we remember our anatomy here, we're looking at all of the vessels that are leading into the hepatic portal system. So we have things like the splanchnic, we have things like the inferior and superior mesenteric, we have the pancreatic veins, the gastric veins. All of them are going to be dumping into the inferior vena cava, which will head into the hepatic portal system, which will then branch out into the sinusoids within the liver itself. These distinct areas that are circled are going to have sensors that are going to be responsive to the amount of 6-carbon and 3-carbon sugars within the plasma, so as to provide for a sensing of hormonal responses that are necessary for triggering the responses that we see after meal, postprandial. And the chemoreceptors that we're looking at here are very similar in terms of the chemoreceptors that we see within the tongue, in terms within the taste buds. And what we're attempting to do is we're attempting to trigger the endocrine response so that we can maintain normal metabolite levels within the plasma. We have two distinct organs that are going to come into play here in terms of digestive function. We have the liver and we have the gallbladder. Both of them are going to be responsible for the production of bile. The gallbladder's bile is going to be predominantly a bicarbonate mixture. However, it can produce some of the lipolytic agents that we see within bile. It could also be producing some of the carboxylases as well as some of the other digestive enzymes. So even though the books and a lot of texts will reference the gallbladder simply as a storage organ, it actually is producing a large amount of bile on its own. It's just not producing as much bile as what we see coming from the liver itself, due to the countercurrent flow within the sinusoid, allowing for the production of bile within normal hepatic functions as it relates to its excretory function. So what is bile? So bile is a crystalline structure that is made up of a hydrophobic and a hydrophilic region that acts as an emulsifying agent. So what it does is it allows for the fat and the water within the alimentary canal, and a majority of the alimentary canal is going to be a hydrophilic region. And a majority of the enzymes that we see digesting are going to be hydrophilic. But the lipids themselves are hydrophobic. And so what we have to do is we have to create an environment that allows for the lipases to interact with the lipids. And so what bile does is it creates a zone that is protected from the aqueous environment of the alimentary canal by basically generating a phospholipid layer around the lipids that are being consumed. And so what it does is it creates this emulsified area so that we're able to digest the lipids, so that the lipids can be processed into something that can be absorbed within the rest of the small intestine, and then transported through the lacteals to the liver for further processing. So what is bile itself? So bile is going to be an alkaline solution that's going to be produced by the liver and the gallbladder. It's going to be involved with digestion of proteins and lipids. It can be involved with the digestion of carbohydrates as well. It's just not as readily digesting carbohydrates as it is proteins and lipids. The bicarbonate that we see being produced is going to help neutralize the gastric juices. But more importantly, it's going to be the emulsifying agent that's going to allow us to go ahead and digest, to absorb fatty acids, cholesterols, and any of the lipid-soluble vitamins that we are consuming within our foods. So how do we go about producing bile? So bile is going to be produced within the hepatocytes. And so what's happening is that the hepatocytes will start to collect chylomicrons, low-density lipoproteins, and other forms of lipoproteins. As they start to absorb these through phagocytotic activity and active transport activity, it's going to acetylate it. As it acetylates it, it's going to strip cholesterol molecules away from the vesicle of the LDL and the chylomicron. It's also going to start to produce free fatty acids. The cholesterol, if it undergoes a 7-alpha hydroxylase reaction, will start to form bile salts. We can have further acetylations that will lead to the cholesterol ester through an esterification acetylation reactions. These cholesterol esters will combine with bilirubin and lichen, as well as the other cholesterols that have not been reduced or esterified, in combination with the bile salts, which have the hydrophobic and hydrophilic areas to it, to form bile. What ends up happening is that the bile fluid in the bile duct is flowing in an opposite direction to what we see coming from the plasma within the sinusoid. And so we end up getting a counter current within the liver, similar to what we saw with the counter current within the nephron, allowing for movement of materials through the hepatocyte into the bile for excretory function. Which, remember, is that the bile is an excretory product, even though it's going to be involved with digestion. This will be distributed through the hepatic bile ducts into the common bile duct to go into the duodenum, or when the duodenum is not being actively secreted into, it will be regurgitated through the cystic duct back into the gallbladder. The products that come about from the reactions on the LDL and the chylomicrons will produce either very low density lipoproteins from the chylomicron or higher density lipoproteins from the LDL molecules, which will go through the circulation to be reprocessed again in a similar fashion. And we talk about that when we look at lipid digestion and absorption. So let's take a look at what's going to regulate bile production and release. So as we start to consume lipids, we start to have an increase of concentration of lipids within the duodenum, which is going to be a secondary signal for CCK release. We combine this with gastric emptying, triggering CCK release to stimulate the gallbladder to release bile from the bladder into the common bile duct. Now, the regular release of CCK without the vagal nerve stimulus will simply just lead to more production of bile, which can become problematic, particularly with people who typically are following the McDonald diet. That is a very high fat diet, particularly animal fat, and in particular dairy fat, people who overconsume milk and cheese and yogurt and ice cream will start to have large amounts of duodenal CCK release without having secondary contractions of the gallbladder due to the means by which the dairy products are being processed. And so what's happening is that these people will start having an overload of bile being produced within the gallbladder. And just like what we talked about in terms of hydration impacting kidney stone formation, we'll start having the salts within the bile start to come out of solution. And as the bile salts come out of solution, they'll start to crystallize, and that's how we get gallstones that will form. So if we get the release of CCK combined with stimulus from the vagal nerve, we're going to start to have contraction around the cystic duct that's going to propel fluid into the common bile duct. We will also have relaxation of the sphincter of Oddi in the duodenal papilla, which is going to lead to release of bile into the duodenum so as to lead to emulsification and digestion of lipids, hopefully enough to cause a inhibition on the signals leading to the release of bile from the gallbladder in the first place. And so that's just one of the pathways that's going to be impacted in terms of the accessory organ. The other accessory organs that we look at here is the pancreas. And what we're going to look at is we'll look at the pancreas in terms of its two distinct functions. So it's going to have an enzymatic function through the pancreatic enzyme release, as well as it's going to neutralize the acidic condition through the release of bicarb. These are going to come from the acinar cells. The other regulation that comes into play comes from the islet cells in terms of sensing of glucose as it relates to absorption of materials from the beta cells. But we'll also be regulating metabolism based off of secretions of glucagon, secretin, CCK, as well as some other peptides that come into play as it relates to hunger response. And so what are some of the pancreatic enzymes that come into play? And once again, there's a big list of enzymes in the study packet. These things include pancreatic amylase, pancreatic lipase, pancreatic trypsin, pancreatic chymotrypsin, pancreatic carboxypeptidase. And then we get two different nucleases that are going to digest nucleic acids. And so let's take a look at the regulation of the pancreas in terms of what's causing it to be stimulated and then what's it going to do in terms of downstream regulation. So as soon as I start thinking about food, the beta cells become stimulated. As soon as I start thinking about food, the pancreatic acinar cells start being stimulated. As soon as I start sensing food within the mouth, the pancreatic acinar cells are being stimulated. The beta cells stop being stimulated at the same level that the pancreatic acinar cells are being stimulated, but they're still being stimulated. We then get the gastric signals of a low stomach pH, an elevated level of CCK, and an elevated level of secretin. All of these stimulate the pancreatic cells to start to release their digestive enzymes as well as their bicarbonate. So we're going to release amylase, we're going to release lipase, we're going to release pancreatic juices, which are going to be predominantly bicarbonate, and we're going to start releasing peptidases, things that are going to digest down proteins. And so what do? We start to neutralize those initial signals, hopefully to the point where we have eliminated those signals following terminus of feeding. Now, part of this signal that comes into play here also heads back upstairs to Hey Dummy, and it says slow down your rate of consuming. We need time to fully digest what has entered. After we've finished digesting what has entered, we now are going to have stuff move into the plasma. And so now we're going to fall back onto the beta cells and hormonal response here. So as we start to sense the food within the mouth, as well as start sensing the food that's being, or the nutrients that have been digested and absorbed, the beta cells start to release insulin. As they start to release insulin, we're going to start to inhibit the initial signal of elevated carbohydrate and lipid levels within the plasma, because insulin is a ubiquitous anabolic hormone that's going to induce the building of glycogen, the building of triglycerides and lipid droplets, as well as the building of amino acid sequences leading to protein accretion, so as to take all of the nutrients that have been digested and absorbed and deposit them into tissues that are insulin sensitive, in particular liver, adipocytes, and skeletal muscle.